Welcome to Fun Facts Online. When we think about a green future, our minds usually jump to vast fields of solar panels or towering wind turbines. And while they are absolutely essential, they are just the opening act in a much bigger show. The true story of engineering a sustainable planet is happening in labs, deep underground, and in the oceans, where scientists are developing a whole suite of technologies that go far beyond the familiar. Today, we're diving into that richer, more diverse world of green energy. We'll explore the power simmering in the Earth's core, the untapped energy of the tides, and how we can turn our waste into watts. We'll even look at how engineers plan to literally clean the air we breathe. So let's get started on our journey into the future of green engineering. Our first stop is deep beneath our feet. We're talking about geothermal energy, the immense thermal power generated and stored in the Earth's molten core. Unlike solar or wind, this is a clean energy source that is available 24 hours a day, 7 days a week, completely independent of the weather. It's the definition of reliable, baseload power. Traditionally, geothermal plants were limited to geologically active areas, places with natural hot springs or geysers. But that's changing dramatically with a technology called Enhanced Geothermal Systems, or EGS. Think of it like this. Engineers drill deep into the Earth's crust, thousands of feet down, to reach hot, dry rock. Then, they create an artificial reservoir by carefully fracturing that rock. Water is pumped down, gets superheated by the rock, and then returns to the surface as steam to drive turbines and generate electricity. EGS is a game changer because it unlocks geothermal potential almost anywhere on the planet, not just in volcanic hotspots. And the innovation doesn't stop there. Engineers are also developing closed-loop geothermal systems. In these designs, a heat transfer fluid circulates through a deep underground pipe loop, absorbing heat from the rock without ever touching it. This approach uses minimal water and virtually eliminates any risk of induced seismicity, making geothermal an even more attractive and scalable option. From the heat within the Earth, we now turn to the power of water, specifically hydropower. Hydropower is one of the oldest and largest sources of renewable energy. But the era of building massive new dams is largely over in many parts of the world, due to their environmental and social costs. So the future of hydropower isn't about building new giants. It's about making existing facilities smarter, more flexible, and greener. A key area of innovation is upgrading old dams with advanced turbine technology. New variable speed turbines, for example, can operate efficiently across a much wider range of water flows. This allows them to quickly ramp their power output up or down, which is incredibly valuable for stabilizing the electrical grid as it tries to balance the fluctuating input from solar and wind power. Digitalization is also playing a huge role. By installing sensors and using AI-driven analytics, operators can optimize every aspect of a plant's operation, predict maintenance needs before failures happen, and squeeze every last kilowatt-hour of electricity from the available water. There's also a growing focus on making hydropower more eco-friendly, with new fish-friendly turbine designs and better fish passage systems to help protect local ecosystems. But here's a truly astounding fact. In the United States, there are over 90,000 dams, but less than 3% of them actually produce electricity. By retrofitting these existing, non-powered dams with generating infrastructure, we could add a massive amount of clean energy to the grid without constructing a single new dam. Now, let's venture out from rivers and reservoirs into the vast, untapped potential of the oceans. The world's oceans are a colossal battery of clean energy. The predictable, rhythmic motion of the tides and the relentless power of waves hold an incredible amount of kinetic energy. Harnessing it is a major engineering challenge. Tidal energy comes in two main flavors. The first is a tidal barrage. This is essentially a large dam built across an estuary. As the tide comes in, water fills a basin. The gates close, and then as the tide goes out, the water is released through turbines. The second and more modern approach is using tidal stream generators. These are basically underwater wind turbines. They are placed on the seabed in areas with strong tidal currents and capture energy from the moving water. They have a much smaller environmental footprint than a massive barrage. Wave energy is a bit more complex, with a wide variety of designs being tested. Point absorbers are floating buoys that bob up and down with the waves, and this motion drives a generator. Overtopping devices are like a ramp. They collect water from incoming waves into a reservoir, which is then drained through a turbine. And oscillating water columns use the rise and fall of waves in a chamber to push air back and forth through a turbine. The biggest hurdles for ocean energy are the harsh, corrosive marine environment and the high costs of deployment. But because water is over 800 times denser than air, ocean energy is incredibly concentrated. And tidal power, in particular, is as predictable as clockwork, making it a potentially very reliable part of our future energy mix. So far, we've covered heat and motion. Next, let's talk about biology and chemistry with bioenergy. This is renewable energy derived from organic matter, or biomass. This can be anything from agricultural waste and forest residue to the organic trash we throw away every day. The modern approach, what we can call waste to watts, goes far beyond simply burning this material. Advanced processes are transforming how we use biomass. For example, gasification uses very high temperatures and limited oxygen to convert biomass into a synthetic gas, called syngas. This syngas can then be burned to generate electricity or even converted into liquid fuels. Another key technology is anaerobic digestion. In this process, microorganisms break down organic waste, like food scraps, manure, and sewage, in an oxygen-free environment. This produces biogas, which is mostly methane. This biogas can be used for heat and power, or it can be purified into renewable natural gas and injected directly into existing gas pipelines. A particularly exciting frontier for bioenergy is the use of algae. Algae can be grown incredibly quickly in ponds, on land that isn't suitable for farming. As they grow, they consume carbon dioxide, offering the potential for a carbon-neutral or even carbon-negative fuel source. The engineering challenge right now is scaling up the cultivation and harvesting to make it economically competitive. From converting waste, we move to a single molecule that could revolutionize our entire energy system: hydrogen. Specifically, green hydrogen. It's being called the Swiss Army knife of clean energy for good reason. Green hydrogen is produced through a process called electrolysis, which uses electricity to split water molecules into hydrogen and oxygen. When the electricity for this process comes from renewable sources like solar or wind, the hydrogen produced is completely clean. The real magic of green hydrogen is its versatility. It can act as a way to store and transport energy. Surplus wind or solar power can be used to create hydrogen, which can then be stored for weeks or months in tanks or underground caverns. When the grid needs power, that hydrogen can be used in a fuel cell or a turbine to generate electricity with only water as a byproduct. It can also be transported through pipelines and used as a clean fuel for heavy-duty trucks, ships, and potentially aircraft. And, crucially, it can be used as a clean industrial feedstock, replacing fossil fuels in hard-to-decarbonize processes like making steel and ammonia for fertilizer. Engineers are working hard to make electrolyzers cheaper and more efficient, and to develop better ways to store and transport hydrogen safely. Now, let's address a more controversial topic: nuclear power. While traditional, large-scale nuclear plants have faced significant challenges with cost, construction time, and public perception, a new generation of nuclear technology is on the horizon, designed to be safer, smaller, and more flexible. The headline innovation is small modular reactors, or SMRs. As the name suggests, these are much smaller than conventional reactors. Their modular design means that components can be mass-produced in a factory and then shipped to a site for assembly which drastically reduces construction time and cost. Their smaller size and advanced safety features, many of which are passive and don't require external power to work, make them suitable for a wider range of applications, like powering a remote community or a large industrial facility. Beyond SMRs, researchers are exploring entirely new reactor designs, like molten salt reactors, or reactors that can run on different fuels like thorium. These advanced designs have the potential to produce significantly less long-lived radioactive waste and can operate at higher temperatures, making them more efficient. Advanced nuclear offers the prospect of a carbon-free, high-capacity, and incredibly reliable power source that can perfectly complement intermittent renewables. Generating clean energy is one thing, but to meet our climate goals, we'll likely also need to clean up the carbon dioxide that's already in the atmosphere. This is where a suite of technologies called carbon capture, utilization, and storage, or CCUS, comes in. The process has 3 steps. First is capture. This involves separating CO2 from other gases at a source, like a cement plant or a power station. Chemical solvents can be used to literally scrub the CO2 out of flue gases. The second step is utilization. The captured CO2 isn't just waste, it can be a valuable resource. It can be used to carbonate drinks, to create synthetic fuels, or even to cure concrete, locking the carbon away in our building materials. The third step is storage. For permanent removal, the captured CO2 is compressed into a liquid, transported by pipeline, and injected deep underground into stable geological formations like depleted oil reservoirs. But the most exciting frontier in this field is direct air capture, or DAC. DAC technologies are essentially giant vacuum cleaners for the atmosphere. They use large fans to pull in ambient air and pass it over materials that chemically bind with the CO2. The CO2 is then released and can be stored or utilized. While it's currently very expensive and energy-intensive, the Intergovernmental Panel on Climate Change estimates that technologies like DAC could be required to remove hundreds of billions of tons of CO2 from the atmosphere by the end of the century to meet our climate targets. Okay, we've talked about a whole portfolio of amazing power generation and cleanup technologies, but none of them can work in isolation. A green future requires a complete re-engineering of the backbone systems that deliver and use energy. First up is energy storage. As we rely more on intermittent renewables, storing energy is critical. Lithium-ion batteries are great for short-term storage, but for grid-scale stability, we need bigger, longer-duration solutions. The most common form today is pumped storage hydropower. It's like a giant water battery. When electricity is cheap, water is pumped from a low reservoir to a high one. When power is needed, the water is released back down through a turbine. Another promising technology is compressed air energy storage. This uses surplus electricity to compress air and store it in huge underground caverns. To generate power, the compressed air is released and expanded through a turbine. Next, we need a smarter grid. The traditional electrical grid was a one-way street, from big power plants to consumers. A green future requires a smart grid, a modernized network that uses digital communication for a two-way flow of electricity and information. A smart grid can seamlessly integrate everything from rooftop solar panels and electric vehicles to large-scale wind farms. It can monitor energy flows in real time to reduce waste, and can even automatically detect and reroute power around outages, essentially healing itself. This also means rethinking our entire approach to how we make and use things. The traditional linear model of take, make, and dispose is incredibly wasteful. The future is the circular economy, a paradigm focused on designing out waste entirely. From an engineering standpoint, this means designing products to be durable, easily repaired, and reusable. It means designing them so their components can be remanufactured into new products at the end of their life. This is systems-level thinking, optimizing a product's entire life cycle. Of course, a sustainable society also depends on clean water. As climate change strains our freshwater resources, engineers are developing incredible new water purification technologies. Advanced membranes made from materials like graphene can filter out even the smallest contaminants with very little energy. New desalination processes are dramatically lowering the cost of turning seawater into drinking water. And some engineers are even using biomimicry, creating artificial aquifers that filter water using layers of sand and gravel, just like the Earth does. Underpinning almost all of these advancements is the power of artificial intelligence. AI is the great orchestrator. It's being used to create more accurate climate models, to optimize the complex balancing act of a smart grid, to monitor deforestation from space, and to accelerate the discovery of new materials for batteries, solar cells, and carbon capture systems. So the journey to a sustainable future is a complex and multifaceted engineering challenge. While solar panels and wind turbines are the vital workhorses, they are just the beginning of the story. The complete picture of a green future is woven with threads of geothermal heat, the power of the oceans, the potential of our waste, the versatility of hydrogen, the reliability of advanced nuclear, and the necessity of carbon removal. This future is supported by an intelligent infrastructure of advanced storage and smart grids, all guided by the principles of a circular economy. The solutions are within our grasp, and engineers are leading the charge to build a cleaner, more resilient, and more prosperous world for everyone. Thanks for tuning in to Fun Facts Online. Join us next time as we explore another fascinating scientific frontier.